Here's a collection of problems that we probably I would have distributed before the second exam. I believe it's mostly in here concentrated on no, I guess it's a combination of circular motion kind of problems, orbital motion, and work energy relationships, energy methods. I saw at least one place where momentum snuck in there. That won't be covered on our second exam, but you'll see that that's a familiar problem anyways from our work in the videos. So let's just go through them one at a time. I'm going to read the problem and then we'll go down to my solutions. We'll start out simply. Here's a 20 kilogram mass dropped from rest. 20 meters above the ground, find its speed just before hitting the ground. Don't use kinematics, use energy methods. So if I go down to my solution to problem 1 here, in this case, I see this is from an old set of solutions. U is just a different notation for potential energy. So this is like saying delta Ke plus delta Pe is equal to 0. So the idea is here, we're taking our system to be the ball plus the earth. Gravity is an internal force, and there are essentially no other forces acting on the moving parts of the system as it moves from initial to final. And so that means the net work done by external forces, there aren't any external forces, I'm ignoring air resistance. Net work done by all external forces is 0, and that's equal to delta Ke plus delta Pe. Okay? Delta Ke is just the difference in the 1/2 mv squared, and the delta Pe is mg y final minus y initial. So it goes down by 20 meters. That minus sign is important there, otherwise you'll take the square root of a negative number in your answer. You can cancel the mass, obviously, from our work before. You should know that the final speed doesn't depend on the mass because everything's accelerating at the same rate, irrespective of mass. Final speed is 19.8 meters per second. All right, up to problem 2. We've got the same mass sliding down a 20-degree frictionless inclined plane. At the bottom, it's 20 meters closer to the center of the Earth, so it slides down a very long inclined plane. It doesn't slide a distance of 20 meters, it slides a longer distance so that it's actually moved 20 meters closer to the center of the Earth. Find the speed at the bottom, and in this case, everything works exactly the same. I could take the same system, just treating gravity as an internal force between the sliding block and the Earth. And in this case, we do have another force acting, the normal force, and we'll take that to be an external force, but the normal force still does 0 work. And so in that case, we can apply the same sorts of solutions and we get exactly the same speed. The solution is identical to problem 1. Problem 3, same 20 kilogram mass is dropped from rest from the height of 2 Earth radii above Earth's surface. Find its speed just before hitting the ground. We're going to ignore air resistance, even though it would have a huge effect. We're just going to imagine the Earth doesn't have an atmosphere in this case. So it's dropped from 2 Earth radii above the Earth's surface, and that means the initial r that we're going to use is 3 times the radius of the Earth. The final r will be 1 times the radius of the Earth, and we'll take our system to be the object dropped plus the Earth with gravity as an internal force, and there aren't any other forces to do work. So again, mechanical energy is conserved. Delta Ke plus delta Pe is equal to 0 because there aren't any other external forces doing work, because air resistance apparently isn't doing anything in this problem. So I have delta Ke is the difference in the 1/2 mv squared. The delta Pe is that expression. I have to really be careful with the minus signs. The Pe final, in the final case, the final r is 1 Earth radius, but we've got to put that minus sign in with the potential energy. So the potential energy is minus g m1 m2 over r, not an r squared in the denominator, just an r. So r final is the radius of the Earth. R initial is 3 times the radius of the Earth. So we have this negative thing minus this negative initial thing. Okay? And all that's equal to 0 when we add it together because there aren't external forces doing work. And after we set them equal to 0, we can divide by m. 0 divided by m is still 0, and there was a common factor of m on this side. And we have to combine together these two things. You can think of it this way. I have minus 1 of these plus 1/3 of these is the same thing as plus 2 minus 2/3 of these. And then when I put it on the other side, that minus 2/3 becomes a plus 2/3. So partly solved is here, and then we can solve for v final by taking a square root. And we get, of course, a huge speed because it was dropped way above the Earth, 9,130 meters per second. Problem 4. Roller coaster has a circular vertical loop of radius 20 meters. A coaster car has a mass of 500 kilograms. If the coaster car has a speed of 5 meters per second at the top of the loop, find its speed at the bottom, assuming there's no friction, and assuming, you're going to need to figure out how far it goes down closer to the surface of the Earth, going from top to the bottom. Let's assume it goes 2 complete radii, right? Going from the top of the circle to the bottom of the circle, it goes through 1 diameter, or 2 times the radius, if the height of the car is negligible compared to the radius. Okay, so that's 4a, and we're also, just so I don't have to flip back up here, in b we're supposed to find the acceleration, magnitude, and direction of the car at the bottom. So let's go down to the solution for 4. In this case, I can take my system. I guess when I wrote this, I was being kind of sloppy about saying what the system was. But let's take our system to be the roller coaster car plus the Earth. Gravity is an internal force. We'll take the normal force from the track on the car to be an external force. But again, just like in the previous problems, the external normal force doesn't do any work, so the net work done by external forces is 0, and that's equal to delta Ke plus delta Pe, the usual expressions there. We're staying near the surface of the Earth, so we just use mgy. And I want to solve for the final speed. Initial is at the top and final is at the bottom, so I'm separating this out to the other side, then canceling some minus signs, and the idea is y final minus y initial is minus 40 meters, but we're going to put that on the other side over here, and it becomes a plus in this particular term. So after all is said and done, you have a greater speed at the bottom, 28.44 meters per second. That sounds pretty fast. Then the next question was, at the bottom of the loop, assuming it's still on the circle, what is its acceleration? And the idea is, as it's coming down the loop, it's actually accelerating along the direction it's going, but at the very bottom of the loop, it's going from speeding up on the way down to slowing down on the way up. So it's right in between speeding up and slowing down. It's neither speeding up nor slowing down, so its direction, it is in uniform circular motion just at that instant, because it's neither speeding up nor slowing down, and that means the tangential acceleration is 0, and the only acceleration component is the radial or centripetal one. We know the formula for that. It's v squared over r. So if I plug in the v we got, that corresponds to the bottom, I square it and divide by the radius of the circle that it's on. It is this magnitude, and its direction is toward the center of the circle. So if you're at the bottom, that's upward toward the center of the circle. Part C. In the case that was described in part A, what weight would a scale read if a 70-kilogram passenger was sitting on it and passed the bottom of the loop? So let's imagine the person sitting on the scale, all of their weight is on the scale, their feet aren't on the ground, but they're sitting off of the ground, so they're only touching the scale. So there's two questions here. As you pass the bottom of the loop, what does the scale read, and what would the scale read if you just took the same scale and stood on it normally without moving at all? That's 4C. So in 4C, while he's moving on the roller coaster passing the bottom, we're going to do radial components. We'll call up the plus x direction at the bottom of the loop. So F net radial equals MA radial. Let's fill that in. If we call upward plus the weight force, the Earth is pulling down on the man, so that's a negative weight force. And the scale is pushing up on the man, so it comes in with a plus sign. Okay, that's the net force along the vertical direction. That's equal to the mass of the man times the acceleration, which is v squared over r, and we already calculated that. So we can just plug in the number that we got above in b and solve for the scale force. The scale force is how hard the scale is pushing up on the man. The man then is pushing down on the scale with an equal and opposite force, and that's what the scale is supposed to read. It reads 1,459.5 newtons. Similarly, off the roller coaster, the only thing that changes about this problem is that the acceleration is 0 on the right-hand side, so the scale just reads, of course, a smaller number. You feel heavier. Your apparent weight is bigger at the bottom of the loop, so we're somewhat close to about half the weight reading, which is the true weight of the person off of it. All right, finally, part D. What is the smallest speed the car could have at the bottom and still make it to the top of the loop? This without falling off. In this case, I guess I'm assuming here, it's unclear what I'm assuming. It sounds like I'm assuming that the car could fall off, which isn't the way roller coasters are normally constructed. If the car is attached on the rail so it can't fall off, then we would take the final speed at the top to be 0, and we want the initial speed to be the thing that we solve for. Whereas if we're assuming the car could fall off the loop and we want it to stay on all the way to the top, it has to have a non-zero speed up at the top. I'm unclear what I'm assuming here, so let's see what my solution says, and we'll just go with that in this poorly stated problem. In this case, I guess I'm assuming it's a normal roller coaster because I'm taking the final state to be the top, initial at the bottom, and I'm going to take the final speed at the top to be 0. So that means it's not able to fall off, but rather it slowly approaches the top and goes asymptotically to 0 speed as it gets closer and closer to the top. So the final speed is 0, initial speed is what we're trying to solve for, and it goes up by 2 radii, in other words, 1 diameter on the way up. So I'm taking my system to be the car plus the Earth. Gravity is an internal force, but the normal force is external, but it doesn't do any work, so the net work done by external forces is equal to delta KE plus delta PE. Solve for V initial. 28 meters per second would just barely get it squeaking to the top. All right, problem 5. A 10 kilogram mass is launched directly up from the ground at a speed of 20 meters per second. Find the maximum height using energy methods. Find its speed after it's gone up only 12.5 meters using energy methods. Problem 5. Okay, so I'm going to take the system to be the mass that shot up plus the Earth, with gravity being an internal force. We're ignoring air resistance here, so there aren't any other external forces to do work, and that's equal to delta KE plus delta PE. Delta KE is the usual expression, and if we're trying to find out how high it goes up before coming momentarily to rest, we're going to take final to be the highest point. So V final is 0. V initial we know from the statement of the problem, and what we want to know is Y final minus Y initial. So this is the change in gravitational potential energy. We'll just call Y final minus Y initial H. Let's solve for H, and when we do that, the mass cancels out, and we get H is 20.4 meters. Finally, in the second part of the problem, we said, well, let's forget about it going all the way to the top. When it's only risen up 12.5 meters, what's the speed of it at that point where it's on the way to the top? And the same kind of analysis, same system, we're going to use delta KE plus delta PE equals 0 in that case, but the delta PE involves a change in Y of 12.5 meters. And in this case, we want to solve for what V final is. When we do that, we get 12.44 meters per second. I'm going to take a little break and then continue. Okay, problem 6. Find the units of capital G without looking them up. This is just to remind you of how you do this kind of thing. We look at the force formula for the gravitational force, Newton's universal law of gravitation. F equals G m1 m2 over r squared, and solve for G. So if I go down to the solution here, we know the units of everything in this equation except capital G. So if I solve for capital G, that tells me the SI units of capital G are the SI units of force times distance squared divided by mass squared. So there you have it over on the right. Problem 7. As the moon orbits Earth, find the force on the moon due to the Earth, acceleration, orbital speed, and orbital period of the moon. So let's just do all of those at once. Force, acceleration, orbital speed, and orbital period. If we, to find the force, we just use Newton's universal law of gravitation, look up the constants that you need on the web or in the back of your book. To find the acceleration, we draw a free body diagram with the moon orbiting the Earth. And a free body diagram for the moon, there's only one force on it. So we do F net equals ma along that radially inward direction for the moon toward the Earth. And that gives us F net equals the mass of the moon times the acceleration along the radial direction. We can solve for the acceleration. Then for the orbital speed, we know that acceleration, because the moon's in uniform circular motion, that acceleration is equal to v squared over r. So plug in r, and you can then take a square root and get v. And finally, to get the orbital period, if we know v, we know that v is equal to 2 pi r over t. That's the old distance over time trick. So plug in the r. Again, this r, the one you want to use for all of these problems, is the distance from the Earth to the moon. Don't use the radius of the moon or the radius of the Earth. They're not relevant for this problem. 0.385 times 10 to the 9th meters. We can say that's equal to the velocity we know and then solve for t. And we get t is about 31.9 days, or of course a huge number of seconds. All right, problem 8. How short would an Earth day have to become for us to feel weightless on the equator? In this case, what we're going to do is, if we're on the equator, we're in uniform circular motion, and the radius of the circle that we're going on is the radius of the Earth. And so what we can do is you do a free body diagram for the person on the equator who's going in a circle of radius, the radius of the Earth. And there's two forces on them. There's an inward force toward the center of the Earth, gravitational force, that's the weight force. And there's also a normal force from, if we imagine they're standing on a scale or something like that, there would be a normal force outward from the radial direction of a normal force or a scale force. And the sum of those two, one positive and one negative, is equal to ma, or mv squared over r, where r is the radius of the Earth. When we become weightless, so the faster the Earth spins, our weight, of course, doesn't change. The Earth is always pulling on us with the same force, but the normal force gets less and less because we need a bigger force in the radial direction to cause that bigger centripetal acceleration if v gets bigger, but r stays the same. So at some point when we feel weightless, that will mean the scale is not pushing up on us anymore. Just like when you're standing normally on the Earth, you feel the Earth pushing up on you. You're pushing down on the Earth. If you feel apparently weightless, then that means the Earth is not pushing up on you from the bottom anymore. So that scale force goes to 0. So the only force on you is your weight force, and that's equal to m times v squared over r. That's F equals ma along the radial direction, radially inward towards the center of the Earth, for the case where you're moving just fast enough so that you feel weightless. The Earth is spinning just that at the right rate. And in that case, your speed would have to be, when we solve this equation for v, doesn't matter what your mass is, that cancels out, and v is 7901 meters per second. Sounds pretty fast, but we're actually moving pretty fast now by virtue of the Earth turning around. We just don't tend to notice it because we're not turning very fast. At this point, you would start to really notice it, right? I mean, if you felt weightless, you would definitely notice it. But we're moving at a pretty good clip right now. In fact, you could calculate that if you really wanted to, see how fast we're moving relative to the center of the Earth, even right now, either at the equator or at Kentucky's latitude. Okay, so that's the speed that we'd have to be moving at, and then we use the old distance over time trick to convert that into the length of time a day would have to be. So if we know our speed, that's equal to 2 pi r divided by t, and we solve for t, and we get about 5,000 seconds, or 1.41 hours. So the period right now is 24 hours. We would have to reduce that to 1.4 hours, so quite a bit of an increase in the rate at which Earth is spinning in order to feel weightless. Problem 9. How much power does it take to lift a 20 kilogram mass vertically at a half meter per second? And how much work is done after 20 seconds? So we can use, in this case, the formula for instantaneous power, which is Fx times Vx. And in this case, we know the v we're going at. We call it upwards direction, the x direction. And then we need the force that we would have to apply to it. I imagine maybe I'm applying the power, I'm outputting the power via my hand, which is pushing up this 20 kilogram mass from underneath. The force I have to apply to lift it at constant velocity has to balance out the weight force because the acceleration is 0. And therefore, Fx would be 20 times 9.8. So the answer is 20 times 9.8 times 0.5 is the amount of power. How much work is done after 20 seconds? Well, remember, power is the rate at which work is being done. So we would multiply that power, that's work per unit times the time, 20 seconds, to get the work that's done. How much power does it take to push a 20 kilogram mass up a 20-degree frictionless inclined plane at 0.5 meters per second? You push along the direction of the plane. So in this case, we're not pushing directly upward, and therefore we're not, the force we have to apply to have it move at constant speed is not the same as moving it vertically. So here is 9 part B. In this case, the applied force has to balance only the component of weight along the direction parallel to the plane. So if we call the direction parallel to the plane x, we're going to do F net x equals max, and there are going to be two forces going into that x F net equals ma equation. And when we do that, that says that the force that we have to apply pulling along the direction of the plane has to balance out that one because ax is 0. We're moving it up at constant speed. And therefore, the conclusion of that is here's fx that we need to apply. I didn't write down the intermediate steps there, but that's the fx you need to apply. And then we know the vx that we're doing, so that we use the power as fx vx, 33.5 watts. And then the work done in 20 seconds, we just multiply by the 20 seconds. Part C of that problem asks, how much power does it take to push a 20 kilogram mass up a 20-degree inclined plane at the same speed if there's a coefficient of kinetic friction? In other words, it's not frictionless. And again, how much work is done after 20 seconds. So in this case, the difference is I have to find out what force is required. It's going to be a different force in this case because not only do I have to overcome gravity, but there's an additional kinetic friction force. So again, let's call up the plane the plus x direction, the direction it's moving, and do F net x equals max. And we'll have three forces that have non-zero x components: my pulling force, the weight force, and the kinetic friction force. And of course, the kinetic friction force depends on the normal force. So I have to then do F net y, where y is perpendicular to the plane direction. F net y equals may. It's also not accelerating along the y direction. That allows me to figure out what the kinetic friction force is, because that will tell me what the normal force has to be. So from F net y equals may, which is 0, I get the normal force. Then I plug that into F net x equals max, and using the kinetic friction force as mu kinetic times n, there are 3 forces that come into there, and it's not accelerating on the x direction either. So that's equal to 0. That allows me to solve for the force that I have to pull with, and then the solution from there is the same as before. I use fx vx to give how much power I have to output with my pulling force, and then multiply that times 20 seconds to get the work that's done in that amount of time, 20 seconds, if I remember correctly. 10. A 10 kilogram mass is launched directly upward from the ground at a speed of 5,000 meters per second. 5,000 meters per second sounds pretty large, so that sounds large enough. If I said 50 meters per second or 5 meters per second, it would be safe to assume that this object stays close enough to the surface of the Earth that mg is the force on it the whole time. But in this case, probably it's going to go up high enough, especially given that we're supposed to ignore air resistance, that we better use F equals g m1 m2 over r squared. Find the maximum height to which it flies, ignoring air resistance. So how high up does it go? So I'm going to take initial to be the launch time and final to be when it momentarily reaches its highest altitude, and figure out how high it goes. So let's go down to the solution for 10 now. Okay, so we're going to use energy methods. I'm going to take the system to be the object that was launched plus the Earth, with gravity being an internal force between the two, and there are no other forces that are acting on it in between initial and final. So that means the net work done by external forces is 0, and that's equal to delta Ke plus delta Pe. V final is 0 because I'm taking the final to be when it momentarily comes to rest at the highest position. And R initial, I've got to use, again, that gravitational potential energy one that's the minus gm1m2 over R, and be very careful with the minus signs. So I'm subtracting them and putting in the extra minus signs there. The initial radius that it's at relative to the center of the Earth is just the radius of the Earth. And the final one is what I'm going to solve for, and then we have to subtract off the radius of the Earth to get the height it goes to. So do a little bit of algebra, plug in those things, and then put this thing on the left-hand side where the 0 was, and we get this equation right here. And then I want to get, you can either cross multiply, or you could say, well, if these two sides are equal, then the reciprocals of them are equal. So that means RF over GME is equal to 1 over this right-hand side. Solve for RF by multiplying by these two things. And you get kind of a mess, but you can plug it into your calculator, and it looks like we get a radius of 7.96 times 10 to the 6 meters, and therefore we have to, from that, subtract off the radius of the Earth to get the height it goes above the launch point. And that gives 1.59 times 10 to the 6th meters. All right, problem 11. Which requires more power? Accelerating from rest to 10 meters per second in 5 seconds, or accelerating from 30 to 40 meters per second in 10 seconds? I tried to make it ambiguous here, so you'd have to actually do the calculation. We already did a voting question that said in going from 0 to 5 or 5 to 10 in the same amount of time, it takes more power for going from the higher speed to an even higher speed. But in this case, we're doing it over a longer period, so it's sort of ambiguous what the power requirements are, or at least I tried to make it seem that way. So let's actually calculate what the power required is. In this case, the net work that has to be done by the force that's outputting the power is equal to the change in kinetic energy if I take my system to be just the car. that power is being supplied by the road ultimately, but or the force that's delivering it to the car is from the road. The power is being output by the engine, of course, but the road is the thing that's exerting the force on the car. So the power output is equal to the change in kinetic energy of the car. So if we do from 0 to 10, we get 50 times the mass of the car. We don't know what the mass of the car is, so I'm just going to leave an m in for that. And to go from 30 to 40, we get 350 times m, and therefore the power output is this amount of work, this net work that has to be done, divided by time. This one would be divided by 5, and I believe this one was divided by 10, but even dividing this one by 10 isn't big enough to make it bigger than this one divided by 5, so the 30 to 40 requires more power in this case. All right, problem 12. Find the escape velocity from the moon. So in this case, I'll take my initial state to be launching it with some unknown speed v radially outward from the moon at the surface of the moon. And final will be the object is really far away, essentially r equals infinity, and its velocity is essentially 0, or its kinetic energy is 0. Let's go down to the solution for problem 12. Okay, so I'm going to take my system to be the object plus the moon, object being launched plus the moon. Gravity is an internal force. There aren't any other forces, so the net work done by external forces is 0, and that's equal to delta KE plus delta PE. Again, this is in a different semester, this is how we wrote kinetic energy and potential energy, but here just imagine this is a KE and a PE, gravitational PE. So in this case, the final state is really far away. That's r equals infinity. R final is infinity. If you divide by infinity or a really large number, you get something very close to 0. And with 0 velocity in the final state, so the final v is 0. And so the sum of these things is equal to 0. And I'm trying to figure out what the initial speed has to be. So putting this on the other side with the 0, and then solving for v initial, we get 2374 meters per second. 13. Find little g on the moon. So the way we always find little g is to write the weight of an object the old way and the new way. So the old way we wrote it was just m times little g, where we're talking about the little g appropriate for the surface of the moon. And the new way, so we set that equal to g times the mass of the object times the mass of the moon divided by r squared. And if we're on the surface of the Earth, that's the surface of the moon, the appropriate r is r of the moon. So when we set those equal to each other, the m's cancel out, the mass of the object cancels out. Okay, so we're going to set those two things equal and solve for g of the moon. And when you plug in the remaining numbers, capital G, mass of the moon, radius of the moon, you get 1.62 meters per second squared, as opposed to our 9.8 here on the surface of the Earth. Okay, problem 14 has a whole bunch of parts, and we're supposed to just quickly assess. You could do any one of these, and I don't know that I did the solutions down below. We'll find out. But what we're asked to do is put a K if we could use kinematics to find the solution, put an E if we could use conservation or energy methods to find a solution. And a lot of these questions are ones that were on that other worksheet that I gave solutions to. We didn't do it in lab this semester, but we would have done it in lab, and it's a collection of energy methods problems posted on the website. Okay, so let's go through them one by one. A box on a frictionless inclined plane, given an initial push downward, it slides down. We're given the mass, we're given the angle. Find its speed after it's moved 1.5 meters down the plane. In this case, we could use either kinematics or energy methods, right? If I were going to use energy methods, I would tend to take my system to be the box plus Earth, with gravity being an internal force, and take the normal force to be external, but then that normal force would do 0 work. Okay, B, Same situation as above, but we're asked to find the amount of time it takes to move 1.5 meters down the plane. In this case, we can only use kinematics because out of those energy methods, energy methods don't ever refer to time. You'll notice that when we do the 1/2 mv final squared minus 1/2 mv initial squared and the change in potential energies, we never get a t appearing in there. And that means the only way we'll be able to do this is with kinematics. So only a k for B. C, a box on an inclined plane is given an initial push downward and slides with friction in this case. Find its speed after it's moved 1.5 meters down the plane. We certainly did problems like this in our kinematics part, so K is appropriate. We could also do it with energy methods too. In this case, again, I would take the system to be the box plus the earth, gravity internal, and my external forces would be the normal force and the friction force. And we would have to calculate the work done by friction as it moves 1.5 meters using mu k times the normal force for that kinetic friction force. D, in this case, it's given an initial push up the plane. It's frictionless, and we're asked to find how far it moves up before turning around. We can do this with either kinematics or energy methods, same system as above, and no work done by external forces because it's frictionless. E, this one sounds very similar, except we're asked how much time it takes to reach the position referred to in D, and there we can only use kinematics because we never get times out of energy methods. F, a box on an inclined plane is given an initial push up the plane and slides with friction. Its mass is 2 kilograms. Find how far it moves up before turning around. So here we could use kinematics or energy methods, similar to the method for the friction case up above. G, half kilogram ball is thrown straight up from the Earth's surface. Find its speed after it's moved 0.25 meters upward. In this case, we could use energy methods or kinematics. For energy methods, you could either take your system to be the ball plus the Earth or just the ball. If you use just the ball, you'd use the work kinetic energy theorem. Or if you do the ball plus the Earth, then you would take gravity to be an internal force and use the potential energy associated with gravity. But it's crucial that since it's only going a short distance upward, the acceleration is going to be constant the whole way through, and therefore we can use kinematics as well as energy method. Similar situation here, we're asked to find the maximum height. Again, we could use either method, and for the energy methods, we could use either of the systems I mentioned before. For I and J, it's the same questions, I believe, but there's a much higher initial speed. We're throwing something up for the moon surface, so it sounds like it's going to go really high. We better not use mgy as the change in potential energy. We better use G minus G m1 m2 over r. And in this case, we can't use, if it's going to go way up high, like 3,000 meters, 30,000 meters above the surface of the moon, we better not use kinematics because the force isn't constant through that whole distance, and therefore the acceleration isn't going to be constant. So we got to use energy methods here, using that more general potential energy formula that we discussed. And so this is find its speed, find its maximum height. So both of these we would do a similar way, and I would use the system ball plus moon with gravity being an internal force. And there's no air resistance on the moon, so we don't have to worry about it being not negligible. 15. Let's just take a peek down here and see what I did for 14. It looks like in 14, I actually went ahead and solved all of these. Now, in a lot of cases, there are choices. Here, it looks like I've done energy methods for part D, but this is just more practice for you. If you wanted to try those problems, you can see how well you fare on them. They're all pretty straightforward kind of problems. Okay. 15. 2 kilogram box is pushed up a 40-degree inclined plane at 1.2 meters per second. Constant speed. We got a coefficient of friction. find the magnitude of the force that's exerted. So for that, we're just going to do F net x equals max. But of course, there's a friction, so we take x to be along the direction it's being pushed. But of course, there's a friction force along the direction it's being pushed, and that depends on the normal force. So in order to find the normal force, we have to sum forces along the y direction. That allows us to solve for the normal force, and then we can use that in the sum of the force of the x components. Both of them equal 0 because it's not accelerating at all, and that allows us to solve for the force that we have to apply to push it up just at a constant velocity. B, find the power output of that applied force. So we're just going to use Fx times Vx to get 25.5 watts. And how much work is done as it moves through 1.7 meters. And there the force we're applying is constant. So we just use our constant applied force times the distance it's displaced, and the force is along the direction it's being pushed. So therefore we don't have to take any component of this along the x direction. It's all along the x direction. And then D asks what? The answer is 0. D asks, what is the net work done by all forces on the box? Yes, the net work done by all forces during it moving those 1.7 meters is equal to the change in kinetic energy of the box, but the box's speed isn't changing, so it doesn't change kinetic energy, and therefore the net work done on the box is 0. 16. A 65 kilogram person in the space station in an orbit of a given radius. What is the speed of the person? What's the weight if they stand on a scale? What's the magnitude of the net force on the person? And what's the magnitude of the acceleration of the person? So you don't necessarily have to do these in this order. In fact, probably the easiest one to do first is just to find the net force on the person. That's g m1 m2 over r squared. So one of those m's is the mass of the Earth, and the radius you're going to use is this, 6.7 million meters to find the net force on the person. The only force is the gravitational force in this case. What is the magnitude of the acceleration of the person? I put the answer to part C equal to ma, and then that a I can solve for given the mass of the person. And what's the speed of the person? Well, that a I've solved for down here in part D can be set equal to v squared over r, where r is the 6.7 million meters, and I can take that square root and solve for the speed. And then finally, b, if the person stands on a scale, what's the weight registered on the scale? It's 0. If you're in the space station, you're in uniform circular motion, and the only force required to keep you there is the force from the Earth. So you're floating inside the space station with a scale floating below your feet, and of course you could push on the scale for a second, but it would go flying away from you. You can't put a constant pressure on the scale, so the scale would reach 0 in this case. I suppose I should just scroll down and look at my solution there. Yes, nothing surprising in this case compared to what I just said. 17. How much force must you exert to move a 2 kilogram mass vertically upward at 3 meters per second? How much force must you exert to move it up at 7 meters per second? How much power? How much power? So same questions for power. If you move a mass up 10 meters, which way will you end up doing more work? Okay, so in this case, in both these cases, the acceleration is 0, right? We're moving it up at constant speed, and therefore the force that I have to apply just balances out the mg. So that means the force that I apply with my hand is an upward force, is 2 times 9.8. So that's how much force I have to apply in both A and B. Doesn't matter that it's moving faster. What matters is it's not accelerating. How much power must I output in those two cases? Well, I have to output more power in B because the power is Fx times Vx if we take plus x to be up. So I take mg times 3 or mg times 7 is the answer to C and D. So it's going to be more power output. Rate of power, or the rate at which I'm doing work, is greater in D. E, if you move the mass up 10 meters, which way will you end up doing more work, at 3 or 7? And the answer is I will do the same, because it's a constant force. We can use the formula for work, which is Fx times delta x, if plus x is up, and the delta x is the same, and the Fx is the same. And so in one case, we do that at work in a very short period of time, that would be C, and in one case in D, and then in C it takes a little bit longer, but we end up doing the same work overall in the two cases. 18. Box sits on an inclined plane with friction at the interface. The box would accelerate downward except for the force applied by your finger on the side of the box facing down the plane. Keeps the box only moving at a constant speed. What is the work done by the finger force on the box as it slides? Is the work done as it slides? And I'm looking for, yes, I didn't read this carefully. It's moving down the plane. I just wanted to make sure that it was going down the plane. Okay, so we want the sign of the work in all 4 of these cases here. The force from your finger. So I'm pushing up the plane while I lower it down the plane. So the work done by my finger is negative because I'm pushing more or less opposite the direction it's being displaced. Force of friction. It's going down the plane, and friction, of course, always goes opposite the direction of motion. So B would be negative work too. C, the normal force, that does 0 work because it's perpendicular to the direction of motion. And D, the force of gravity, well, the force of gravity is more or less along the direction it's going. In other words, gravity's trying to pull it down the plane, and it is going down the plane, so gravity does positive work. Fx times delta x. If we take delta x to be going down the plane, it's the positive x direction, then Fx would be positive for gravity. 19. A record rotates in the horizontal plane of the Earth. Here's a 20-gram coin sitting at a point 9 centimeters away from the center. And it's rotating with the old phonograph record. Between the coin and the record, there's a static and kinetic coefficient of friction given. If the record rotates at 15 RPM and the coin doesn't slip, what's the coin's speed? And in this case, well, let me read all of them, then we'll just get down to the solution. B, if it rotates at that same rotation rate, what is the magnitude of the horizontal friction force that the record applies to the coin? Notice it's not slipping in that case, so it's definitely static friction, but not the static friction maximum force. We have to balance forces, or in other words, use F net equals ma to figure out what the force is in this case. It's probably not about to slip. This is just a randomly given 15 RPMs. Probably it's not about to let go, so we shouldn't use the mu static times n. C, if we adjust the rotation speed of the player, what's the largest speed the coin can have and still not slip? So this is 19. This is an old exam problem. Okay, so if it's rotating at 15 RPMs, always when we get RPMs and we want speeds, we use the distance over time trick. And so if it goes 15 revolutions in 1 minute, we know that that 1 minute or 60 seconds is the time we'd like to use. How far does it go? Well, it goes 15 revolutions. 15 times 2 pi r, so that gives us the speed. For the same situation, 15 RPMs, what's the magnitude of the horizontal friction force? So in this case, I don't have a free body diagram drawn here, but if you drew a side view of the coin, an edge-on view of the record, there would be an upward normal force, a downward weight force, and then a friction force pointing towards the center of the record. And actually, this is mislabeled here. This should be Fs. It's a static friction force. The coin's not slipping here, so I should really label it as Fs. But in any case, if I do F net equals ma along the radial direction, the normal force and the weight force don't contribute along the normal direction, and so the only force along the normal direction, the radial direction, is the static friction force. So the static friction force is equal to mv squared over r. We already found our v, we know r, we know m, so we can get the force that static friction is. And that's less than the maximum it can exert. Now we're going to slowly speed up the record's rotation rate and find at what speed does it break free. So when it breaks free, in other words, if static friction is just barely hanging on, and if I speed it up anymore, it's going to break free, that means the static friction force, again, this is mislabeled, that should be an S there, is equal to mu static times the normal force, right? And the normal force balances out the weight force. You can get that from, vertical components of F net equals ma, where a is 0 along that direction because it's not accelerating vertically, in other words, perpendicular to the direction. And that gives me the static friction force, and it looks like I dropped the ball in writing the answer to this. We're supposed to find the largest, the speed. This indeed is the required static friction force, but then I set that equal to m times v squared over r and solve for v. So you'd have to do that additional step here. And I got so excited that I solved for that static friction force that I forgot to finish solving the problem. All right. Back up to problem 20. A 20 kilogram box is pulled up a frictionless 20-degree inclined plane by 100 Newton force parallel to and directly up the plane. So we're pulling with a rope parallel to the plane. Find the work done as it moves 3 meters up the plane. Find the work done by the applied force, by the gravitational force, and find the final speed of the box after it's moved 3 meters up the plane if it starts from rest. And we probably use energy methods, even though we could probably use kinematics there. Let's use energy methods. So in this case, the idea is the forces don't balance out. It's accelerating up the plane, or at least that's the implication here. So let's first figure out what that, we don't necessarily need to know what that acceleration is, but we could figure it out if we wanted to use kinematics. Let's use work energy methods. So in this case, we're supposed to first find the work done by the applied force on the box as it moves 3 meters up the plane. We know how big the applied force is 100 newtons, and it's along the direction it's moving, so I just use Fx times delta x. 100 times 3 is 300 joules. Find the work done by the gravitational force. That's negative work, and there it looks like it's a mistake here. This should be negative work. Gravity's pulling in the direction down the plane while it's moving up the plane, so I need to find the component of the gravitational force along the direction of the plane, and it should be negative. So in this case, I'm explaining this in a little bit of a confusing way, or at least it's not that similar to what we were doing, the way I maybe have explained other problems. I took the component of the displacement along the direction of the gravitational force, but usually the way I've been explaining it is to calculate the work done by gravity, we would do the component of the gravitational force along the direction it's being displaced, so along the plane direction, and then put a minus sign in front of it and multiply by the distance it moves. It should be a negative work that gravity does. Find the final speed of the box after it moves 3 meters up the plane. Here I've actually put in the minus sign there correctly. So I'm going to use the work kinetic energy theorem. So taking our system to be just the box, the net work done by all forces on it, which is the work done by the pulling force minus the work done by gravity. In this case, the normal force doesn't do any work, so I could put a plus 0 on there, but that doesn't affect anything. And that's equal to the change in kinetic energy. And it is pulled, I'm assuming it says somewhere in the problem that it starts from, oh, it does say it starts from rest. So its initial velocity is 0 and final velocity, that's what we're solving for. So that's problem 20. Problem 21, hey, thankfully I don't have to flip back up to the problem statements because they're written here. Two people push in opposite directions. Somehow this box is on a frictionless surface, but somehow they're standing on something with friction. The box is originally at rest at point P, center of the box, moves to the right and ends up with the center at point Q. Describe qualitatively how much work is done on the block by person 1 relative to that done by person 2. So it starts at rest, it ends up at rest. That means the net work done is 0 because the change in kinetic energy is 0. It starts at rest and ends at rest. 2 is doing negative work, right? The box is moving in this direction, but 2 is pushing in that direction. So 2 does a certain amount of negative work, whereas 3 does a certain amount of positive work, and they're equal and opposite to each other. So the magnitudes of the works are the same. I wouldn't, apparently I did a sloppy job of writing up these hastily done solutions here because the works aren't equal, they're equal and opposite, right? 2 does a negative work, 1 does positive work, but their magnitudes are equal. 22. A marble is dropped from the top of a skyscraper. Is the work done by Earth's gravitational force on the marble equal to, smaller than, or larger than the work done by the marble's gravitational force from Earth? I'm hesitating because I'm reading this. The work done by Earth's gravitational force on the marble compared to that done by the marble's gravitational force on Earth. So in these cases, we're talking about the force of the marble on the Earth equals the force of the Earth on the marble. That's Newton's third law. The Earth is hardly moving at all, so the marble's force is hardly doing any work, whereas the marble is moving a lot, so the Earth's force on the marble does a lot of work. So the Earth's force on the marble does more work on the marble than the marble's force does on Earth, because Earth is not moving essentially at all. It does move a tiny bit, but it's negligible because of its large mass. It just doesn't accelerate very much. 23. Is it possible to have a non-zero net force on an object that does no work on the object? Give an example of this for an object going in a straight line and an object on a curved trajectory. So in the first case, we're asking, is it possible for a non-zero net force? That means we add up all the forces, they don't add up to 0, that does no work on the object. And so in this case, it certainly is possible. I'm not sure my picture here makes much sense to me, but it's possible that I could have, for example, something in projectile motion, right? An object in projectile motion, it goes over the top of an arc going from initial on the way up to final on the way down. And let's take initial and final to be the same height, for example. Then the net force, because it's accelerating downward, the net force is just the weight force. It's essentially down the whole way. So the net force is not 0, and yet the that net force does 0 work, because if our initial and our final are at the same height, one on the way up and one on the way down, the kinetic energy will be the same at those points. In other words, the speed is the same, so the kinetic energy is the same, and therefore, well, I guess that's what I'm explaining is a case of the object going along a curved trajectory. Rather, and my example here is also if you have uniform circular motion, there's a net force that is non-zero. It's certainly not constant in those cases, but here's another non-zero net force acting as it goes around this arc, and its change in kinetic energy is 0, and therefore the net force is 0. If something is moving along a straight line, I could use the example I did before where I instead of throwing something along an arc, I throw it straight up and take initial to be when it's at a certain height on the way up, final to be when it's at a certain height on the way down. There's a non-zero net force acting the whole time between there in the direction downward, and yet the change in kinetic energy is zero because it has the same initial and final velocity, and therefore the net force does no net work on the object. All right, 24. Wow, this is a slog getting through all these, but hopefully we're almost done. I think there's only 27. Identical constant forces push mass A and B continuously from the starting line to the finish. So constant force. Mass B is twice that of A. Okay, so B is going to take longer because that same force doesn't accelerate as much. It takes longer to get to the finish. If A is initially at rest and B is initially moving to the right, which mass has the larger change in kinetic energy between start and finish? So in this case, the same amount of work is done on them, right? Because we're applying the same force and they move through the same displacement between start and finish, and therefore, assuming my force that I'm applying to it is the only one doing work, the weight force and the normal force wouldn't do any work. So the net work is the same, and therefore the change in kinetic energy is the same. So in A, it would be the same for both of them. Which one has the larger change in speed? I think this is somewhat of a difficult question to answer. Where is this? Yeah, I did make a somewhat complicated argument here. I would say let's just exclude B. It's worth thinking about, but my argument was a little bit more complicated than I anticipated, I think, when I wrote the problem. So you can take a look at that. Here I'm saying at least a case I can make clear is when the masses are actually equal, and then you can see that one of them has a larger change in speed than the other one. But I would just say forget about that problem. 24b. I don't know if in the version I've given to you that maybe I deleted that. I have a memory of taking it out at some point. In any case, ignore B. 25. Car drives at constant speed on a circular track of radius r, which is banked inward at an angle theta, the usual situation. Find the normal force that the track provides and the required friction force that keeps the car from slipping as a function of v, r, and theta. So in this case, this is one of those symbolic problems where I assume I know v and I know the radius of the track and the angle of banking. We're just supposed to keep them in there rather than plugging in numbers. This probably isn't the best practice for doing things that you would find on the exam, but in any case, let's look at the analysis down here. 25. So in this case, here's my free body diagram for the car. And I'm sorry, I have to go back and look at what the question was again. Find the normal force provides and the required friction force on the tires that keeps the car from slipping as a function of those. So we don't really know. The thing we have to think about that's a little bit complicated in this problem is we don't know whether the friction force, and again, this should be labeled as a static friction force right here. This should be a static friction force. If the car is really whipping around, the static friction force has to push inward to give it a, to keep it from sliding outward. Whereas if the car is just sitting there on the track or moving really slowly, the static friction force has to push outward, radially outward, or at least outward up the plane, because the car kind of without friction would want to slide toward the inside. So we don't really know what this static friction force, should be labeled as Fs, is going to be. But these are the three forces, and so if I take it to be pointing downward, if we solve for that static friction force and we find it's negative, we know that means that it has to be outward. And then what I can do is just take x to be along the direction, x is along the direction toward the center of the circle, and y is straight up and down. Why am I doing that? Because I know the acceleration direction is toward the center of the circle. And I do F net x equals max. Take the relevant force component, set it equal to mv squared over r, and F net y equals may. And in that case, I have three forces, and they add to zero because it's not accelerating along the y or vertical direction. And you can solve that. It's kind of a mess. I wouldn't worry too much about the algebra there, but the solution is given there. I certainly wouldn't give that kind of problem on the exam. It's all in terms of symbols, and even that problem without the symbols, if you have the numbers, is somewhat of a mess to solve. All right, two more. A light spring of certain spring constant is oriented vertically with the bottom attached to Earth, and we put a certain mass ball on it, and the ball can't roll off the thing we place it on, but it's shaped so that it stays in there as long as it doesn't roll to the side. The ball is not glued into the cup. That means if we push it down and release it, it might get shot off the cup if we push it down far enough. If the ball, so I'm looking at A now, if the ball is pushed down so the spring is compressed 1/4 of a meter below its relaxed length and released from rest, how far above the top of the spring does it fly? Okay, so that means relative to what we usually call x equals 0, the spring equilibrium condition, what is the height of the ball above the top of the spring? And B, if we don't push the ball down far enough, it will never leave the spring on the way up. What is the minimum distance the ball can be pushed down so that the ball is pushed down any more than this, it will separate and fly upward from the spring. The idea so in both these, we're going to use energy methods. And in A, we're going to take the spring final potential energy to be 0, and that means the ball will have gone up. And we're going to try to find, y final. In B, we're going to set y final equal to 0 and see what that minimum distance is. So let's go down and look at the solution to 26. So here I'm going to take my system to be the ball plus Earth, spring, and gravitational potential energy are those forces are internal forces, so we'll associate potential energy with them. Since I'm going to call plus y upward, let's write the spring potential energy as 1/2 ky squared, with the convention that y equals 0 is when the spring is relaxed. That's what the picture is indicating over here. Okay, and in that case, on the way from its initial compressed position to its final, has flown off the top and has speed 0 position, it starts at rest, and I'm sorry, we're supposed to, in part A, find its speed as it passes the spring equilibrium position. So in this case, the final condition is going to be when y equals 0, we want to find what v final is. So, net work done by all external forces. There aren't any external forces doing work on the moving part of the system, the ball in this case. So they're all internal forces for which we have a potential energy change. Here's the changing kinetic energy. Initial speed is 0. The final y position is 0 because the spring is relaxed. We have to take y equals 0 to be when the spring is relaxed. And the distance it moves up, y final minus y initial, is 1/4 of a meter. So if we plug all that in, we're able to find v final is 55.9 meters per second. Apparently it's a strong spring. 500 newtons per meter is pretty strong. So if that's the speed it has when it passes this height right here, then we could either use a little kinematics calculation or do work kinetic energy, the work energy relationship with this being initial and the final being at the top. There's actually an easier way to solve this problem. We could just, in one step, here I've done it in 2 steps. In one step, we could take initial to be the compressed position, final to be at the maximum height. So both V initial and V final are 0, and the final spring potential energy is 0 because the spring is all relaxed there. The initial one, there's an initial spring potential energy, so we have to plug that in just like there. And the delta y that we want to find out, we could write as 0.25 meters plus h, where h is what we want to find out. So there's a way to do this in 2 steps, but for some reason I did it in, you can do it in 1 step. I did it in 2 steps by first taking initial to be compressed, final as it passes the relaxed position, and then initial is relaxed and final is at the highest height. That's how I did the solution here, but you can do it in 1 step, just going directly from initial at rest to final at the highest height at rest. Now we want to find out if we push it down below a certain height, it will actually jump off. But if we only push it down a tiny bit, it won't jump off the spring. What's the minimum distance we can push it down to make it jump off the spring? So we're going to take initial to be that compressed distance, and that's going to be our unknown, and final to be it makes it to the equilibrium position, because if we push it down any more than that, it's going to go past the equilibrium position. So our final position is going to be speed equals 0. In other words, it just barely makes it to and stops at the spring equilibrium position, which is y equals 0. And again, so in this case, initial, it's at rest, final, it's at rest, and we want to solve for y initial. And unfortunately, it looks like we have a quadratic equation here. We do, but there's no constant term, so we can actually solve it by factoring. And there are 2 solutions. We can either compress at 0 distance, and if we compress at 0 distance, then if you let go of the ball, it will bounce down and come just barely back up to rest at the equilibrium position. That's not the answer we were looking for. Or the other one we get by factoring is how far we can press it down so that it just barely makes it off the top of the spring. It's just about to jump off. Whew. Finally, problem 27. Hey, this looks like a ballistic pendulum, except I don't think we have to use any momentum methods here. In this case, the block is hanging there, and someone uses a bat to give it a whack to the right, and so it's given an initial speed v to the right, and to what maximum height h will it rise. So we don't need to use conservation of momentum here. Here, mechanical energy is conserved between there and there for the system consisting of block plus earth, where gravity is an internal force, because those those strings are never doing any work. They're always pulling in a direction which is perpendicular to the direction it's moving, so the string force doesn't do any work. So we'll take that system to be our system and use conservation of mechanical energy. There are no external forces that do any work, and that's equal to delta KE plus delta PE, and we can find what y final minus y initial is. We call it h. We can solve for h and figure out what it is. All right, that was a marathon session, but we are done, and I hope that was helpful for you.